You've heard the tagline, "In space, no one can hear you scream." It's a great movie quote, but it's physically lazy. Most people think sound stops in a vacuum because there's nothing there, like a car running out of road. You think the sound wave travels out of your mouth, hits the emptiness, and just fades away. Wrong. That is not what happens. The reality is much more violent. If you were floating outside the ISS without a helmet, ignoring the freezing and the suffocation for a second, and you screamed with every ounce of air left in your lungs, the sound wouldn't fade. It would be strangled inside your own throat. Because sound isn't a thing you release. It's a relationship. It's a handshake between atoms. And when you remove the air, you aren't just removing the road. You are breaking the fundamental link that allows the universe to talk to itself. Wait, did you catch that? The universe talking to itself? We are going to look at what sound actually is. Not the wiggly lines in a textbook. I want to show you the mechanical brutality of silence. By the end of this video, you won't just understand vacuums. You will never listen to the world the same way again. Let me show you the trick. You remember this from 8th grade science class, right? The teacher puts a ringing alarm clock inside a glass jar. They flip a switch. A pump starts wheezing. The air gets sucked out. Slowly, the ringing gets quieter and quieter until finally, silence. You can see the little metal hammer still smashing against the bell. It's moving furiously, but you can't hear a thing. The teacher looks at you and says, "Sound needs a medium to travel." You write it down. You pass the test. Stop. That explanation is lazy. It's practically a lie. The word medium is boring. It sounds like a t-shirt size. It implies that the air is just a container, a passive box that carries the sound like a package. That is not how physics works. Here is the part nobody tells you. Sound isn't a thing that travels through the air. Sound is the air itself. Think of it like this. Imagine an invisible bridge connecting your ear to that alarm clock. When the clock rings, it doesn't throw a sound ball across the bridge. It grabs the bridge and shakes it. The vibration is the message. Now look at the vacuum again. When we pump the air out of the jar, we aren't blocking the sound. We are dismantling the bridge. We are removing the bricks one by one. The alarm clock is still stomping its feet. The energy is there. The intent is there. But the road is gone. Here's the thing. If you stand at the edge of a cliff and scream at a friend on the other side, they don't hear you. Not because your scream wasn't loud enough, but because there is physically nothing between you to shove. So the bell jar experiment isn't about silence. It's about isolation. But this raises a weird question. If the hammer is hitting the bell and the bell is vibrating, but the vibration can't leave the bell, where does all that energy go? It can't just vanish. That breaks the laws of physics. To answer that, we have to shrink down, way down. Okay, zoom in. I want you to close your eyes. Imagine the air in this room right now. You probably picture it like a gentle, empty haze. Maybe a few dust motes floating in a sunbeam. Peaceful. Wrong. If you had microscopic supervision, you wouldn't see peace. You would see a riot. The air around you is a mosh pit. Billions of nitrogen and oxygen molecules are smashing into each other at 1,000 miles per hour. They are violent. They are chaotic. This is the medium we talk about. Now, imagine you are one of those molecules. You're floating, minding your own business. Suddenly, wham! Something hits you from behind. That's sound. Sound is nothing more than a coordinated shove. When that alarm clock hammer hits the bell, the metal flexes. It snaps outward. And when it snaps out, it sucker punches the air molecules right next to it. It says, "Move!" Those molecules panic. They have nowhere to go. They are crowded. So they smash into their neighbors. and their neighbors smash into their neighbors. It's a domino effect, but instead of falling down, they are shoving forward. This is the trick. The molecules themselves don't travel across the room. The molecule that hit your ear didn't come from the bell. It was already next to your ear. It just got shoved by the guy next to him. It's like a stadium wave. The people don't run around the stadium. They just stand up and sit down. The wave moves. The people stay put. But in a vacuum, this is where the horror sets in. In a vacuum, you take the mosh pit and you empty the club. Now when the bell snaps outward, it punches nothing. It swings its fist and there is no air molecule to hit. It's a phantom punch. It whiffs. And because it doesn't hit the first molecule can't hit the second one. The chain reaction dies before it even takes its first breath. But wait, if the molecules are bouncing around at 1,000 miles per hour, why isn't sound instant? Why does it take time to hear thunder after lightning? Because the mosh pit is sloppy. This is the part that usually breaks people's brains. Light is instant. Almost. You flip a switch, the room lights up. It feels immediate because light doesn't wait for anyone. But sound? Sound is slow. Why? Because sound is a negotiation. The air isn't a solid block. It's squishy. Think of it like a giant slinky. If you stretch a slinky across the room and flick one end, the ripple doesn't teleport to the other side. You watch it crawl. It compresses, expands, compresses, expands. That crawling motion is exactly what air does. When a molecule gets shoved, it doesn't instantly shove the next guy. First, it has to accelerate. Then it has to travel the microscopic gap between them. Then it collides. Then the next guy has to accelerate. It's a relay race with 1 billion handoffs. Each collision takes a tiny fraction of a second. But when you add up billions of collisions across a football field, that delay becomes noticeable. That delay is what we call the speed of sound. Here's the visual. Imagine a crowded subway car, packed shoulder to shoulder. If the train lurches forward suddenly, the people in the back don't feel it instantly. The first person falls into the second falls into the third. A wave of people falling moves down the car. That wave has a speed. It's determined by how fast people react and how tightly packed they are. In air, that speed is roughly 767 miles per hour. But in water, the molecules are packed tighter. The subway car is jammed. So when one moves, the neighbor feels it almost instantly. Sound travels 4 times faster in water. In steel, even faster. The atoms are locked in a rigid lattice. You hit one end of a steel rail with a hammer, and the sound races to the other end at 13,000 miles per hour. So the denser the material, the faster the news travels. But go back to the vacuum. In a vacuum, the density is 0. The subway car is empty. The slinky is gone. There is no next guy. There is no handoff. There is no negotiation. There is just the end of the line. Okay, you see the setup now. Sound is a collision. It needs someone to shove. And it takes time to shove them. But let's look at the terrifying part. Let's look at the exact moment where sound dies. Imagine you are a molecule right at the edge of the vacuum. One side of you is crowded with billions of other air molecules. The other side is nothing. Just black, empty void. The bell rings inside the jar. The vibration travels through the metal of the bell. The atoms in the metal are screaming, vibrating violently back and forth. They reach the surface of the bell. They punch outward into the nothingness. And they miss. They swing, and there is no air molecule there to take the hit. It's like throwing a punch in a dream. You put everything into it, and your fist just sails through empty space. The energy doesn't transfer. It stays trapped inside the bell. This is the cliff's edge. It's not a gentle fade. It's a hard wall. The sound wave doesn't leak out into the vacuum and get quiet. It hits the boundary of the material, the edge of the bell, and bounces right back inside. It reflects. Think of a pool table. If you shoot a ball towards the edge, it doesn't fall off the table and keep rolling on the floor. It hits the cushion and bounces back. That is exactly what happens to sound at the edge of space. The bell keeps ringing. The metal keeps vibrating. The energy stays inside the object, bouncing around like a trapped echo until it turns into heat. So if you were floating next to that bell in space, you wouldn't hear a whisper. But if you touched it, if you pressed your helmet against it, boom! Suddenly, the cliff disappears. You become the medium. You become the bridge. But without that contact, the sound is trapped in a solitary confinement cell made of its own inability to leave. Wait. If the sound energy stays inside the bell, doesn't the bell get hot? Yes, it does. Here is the question that kept me up at night as a student. You remember the law of conservation of energy? Energy cannot be created or destroyed. It can only change form. So if I ring a bell in a vacuum, I am putting kinetic energy into the system. I am hitting it with a hammer. I am feeding it energy. Normally, that energy leaves the bell as sound waves. It pushes the air. It escapes. But if the air is gone, where does the energy go? It can't just evaporate. That's illegal in physics. It stays. The bell becomes a prison for its own vibration. The sound waves bounce back and forth inside the metal, desperately looking for an exit. They are trapped like a bouncy ball in a small room. And every time they bounce, a tiny bit of that motion gets disorganized. The orderly ding becomes chaotic jiggling. Do you know what chaotic jiggling is? Heat. The bell gets warmer. If you could ring a bell in a perfect vacuum forever, it would eventually heat up. The sound energy literally cooks the metal from the inside out because it has nowhere else to go. So when people say space is silent, they are missing half the story. Space is silent, but it is also hot with frustrated energy. This is the energy heist. The vacuum steals the sound and turns it into heat. But wait, there's a loophole. If sound is just vibration, and light is also vibration, why can light travel through a vacuum? Why can we see stars but not hear them? Because light cheats. Light isn't a mechanical wave. It doesn't need a medium to push against. It is an electromagnetic wave. It creates its own electric and magnetic fields as it travels. It is self-sustaining. It builds its own road as it drives. Sound is lazy. Sound needs a road built for it. But what if I told you the universe has a way to build that road, even in the emptiness of space? Remember what I said earlier? Sound is the universe talking to itself. But most of the universe isn't empty. It's full of plasma. Here is the part nobody tells you about space. It's not a perfect vacuum. It's a messy, thin soup of charged particles. It's a vacuum compared to the Earth's atmosphere. But it's not nothing. There is stuff out there. And where there is stuff, there is sound. The sun is screaming. It is a violently boiling ball of gas. It has giant convection cells the size of Texas, rising and falling. It has explosions that release more energy than 1 billion nuclear bombs. If sound could travel through the vacuum of space like it does on Earth, if there were enough air between here and the sun, do you know how loud it would be? You wouldn't just hear a hum. It would be 100 decibels. On Earth, 93 million miles away. That is as loud as a chainsaw right next to your ear, or a rock concert, or a jet engine taking off. If space wasn't mostly empty, we would all be deaf by now. But the sun isn't silent. The sound waves are there. They travel through the plasma of the sun's atmosphere. They ripple through the solar wind. But they hit the wall of the vacuum before they reach us. They hit the disconnection. The density drops so low that the wave can't propagate. The handshake fails. The particles are too far apart to pass the message, so the sound stays trapped near the sun, or it dissipates into the nothingness. But wait, we have recorded sounds from space, right? You've heard the spooky whistles of Jupiter, The black hole chirps. How did we hear those if sound can't travel? Because we cheated. We turned radio waves into sound waves. Those recordings aren't sound. They are electromagnetic data. We convert the frequency into something our ears can process. It's like reading sheet music. You aren't hearing the piano, you are translating the symbols. But there is one place where the sound is real, and it is terrifying. Here is the thing. Astronauts don't hear space, they feel it. You are in your suit. You are floating outside the ISS. You are in a vacuum. The silence is profound. But then you grab a handrail. Suddenly you hear a clunk. You hear the metal groan as you pull yourself forward. You hear the whir of a motor inside the station wall. Why? Because sound doesn't need air. It needs matter. And when you grab the handrail, your glove touches the metal. The vibration travels from the station into your glove, into your hand, up your arm bones, into your skull, and directly into your inner ear. This is bone conduction. Your body becomes the bridge. You bypass the air entirely. You become the medium. This is why your voice sounds weird when you hear a recording of yourself. When you speak, you hear your own voice through the air and through the bones of your skull. It sounds deeper to you, richer. But on a recording, you only hear the air part. It sounds thin, whiny. Now imagine being in space. If your radio fails, you can touch helmets with another astronaut. The air inside your helmet vibrates the glass. The glass vibrates their glass. Their glass vibrates the air inside their helmet. You can talk without radios, without electronics. Just two humans huddled in the void, pressing their heads together to bridge the gap. It's intimate. It's desperate. But what happens if you don't touch? What happens if you are just floating? This is the nightmare scenario. If your suit fails, if the air rushes out, the last thing you hear isn't a scream. It isn't an explosion. It is the sound of your own blood boiling. And then, nothing. Because the sound waves inside your throat have no air to push against. Your vocal cords can vibrate all they want. But without air, they are just flapping in the void. You scream, but no sound comes out. Okay, this is where it gets heavy. What does silence actually look like? You might think it's just a flat line on a graph, a zero. But in physics, it's not that simple. Silence is a process. It is a decay. When you cut off the source of sound, the waves don't instantly vanish. They linger, they echo, they dampen. Think of it like ripples in a pond. You throw a rock, the ripples spread out, they hit the shore, they bounce back, they interact, they fade. In a vacuum, that process is reversed. It's not just that the sound stops, it's that the medium itself fails to carry the message. The silence is imposed. It is a blockade. Mathematically, we call this attenuation. Sound waves lose energy as they travel. In air, they lose a tiny bit with every meter. In water, even less. Whales can talk across entire oceans because water carries the energy so well. But in a vacuum, the attenuation is infinite. The energy drops to zero instantly at the boundary. It is an exponential curve that crashes into a wall. And this brings us to the weirdest thought of all. If sound is just vibration, and everything in the universe vibrates, does that mean the universe is technically loud? Yes, but not to us. Our ears are pathetic. We can only hear a tiny sliver of the spectrum, 20 hertz to 20,000 hertz. That's it. Anything lower? Subsonic. Anything higher? Ultrasonic. Dogs hear higher. Elephants hear lower. But the universe? The universe is playing a song that is so low, so deep, and so slow that a single note takes millions of years to play, and we are deaf to it. Let's talk about the lowest note ever played. In 2003, astronomers pointed the Chandra X-ray Observatory at a cluster of galaxies called Perseus. What they found wasn't just light, it was ripples. Giant concentric ripples in the hot gas surrounding a supermassive black hole. They analyzed the ripples. They measured the distance between the peaks. They calculated the frequency. and they realized it was sound. But it wasn't a chirp, it wasn't a roar, it was a B flat. But not a B flat you could hear. This note was 57 octaves below middle C. A normal piano has about 7 octaves. This note is so deep that the frequency is 1 oscillation every 10 million years. That is the sound of a black hole humming. Why could we hear it? Because the galaxy cluster isn't empty. It's filled with hot gas. It's a medium. The sound waves are traveling through it. They are heating up the gas. They are keeping the galaxy from collapsing. This is the mind-blowing part. Sound isn't just something we hear. It is a physical force that shapes the universe. Without these sound waves, the gas in the cluster would cool down. It would condense. It would form too many stars too quickly. The galaxy would burn itself out. But the sound waves keep the gas hot. They keep the galaxy alive. So sound literally saves the universe from dying. Think about that for a second. A hum so deep and so slow that it takes millions of years to vibrate once is holding an entire galaxy together. It is the heartbeat of a monster. But here on Earth, we are deaf to it. We are too small. Our ears are tuned to the tiny, frantic vibrations of air molecules. We miss the big picture. We miss the cosmic symphony. So, we come back to the scream. In space, no one can hear you scream. But why does that matter? Why is that thought so terrifying? It's not because we are afraid of the quiet. It's because we are afraid of being alone. Sound is proof of connection. It is physical evidence that you are not isolated, that the air around you is touching something else, that you are part of a system. When you speak, you physically touch the person next to you. You push the air pushes them. It is an invisible hug. But in a vacuum, you are truly alone. You can shout, you can cry, you can rage, but your energy has nowhere to go. It stays with you. It dies inside you. The silence of space isn't peaceful. It is the ultimate rejection. It is the universe telling you that you are disconnected. But here is the beautiful part. We found a way to bridge the gap. We built radios. We built ships. We built sensors. We learned to listen to the light. We learned to hear the gravity waves. We learned to touch the stars even when we couldn't hear them. We refused to accept the silence. And that is what being human is. It is finding a way to shout across the void even when physics says it's impossible. So the next time you hear a bell ring, or a friend laugh, or a car honk, don't just hear it, feel it. Feel the air shoving against your eardrum. Feel the invisible bridge connecting you to the world, because that connection is fragile, and out there in the dark, it doesn't exist. So cherish the noise. It means you're not alone. And if you learned something new today, make some noise on that like button, because I'm listening.